Hi to all, how are you? Now, today, class 10 electricity chapter I am going to continue. Right? The class 10 electricity chapter I am going to continue. In that electricity chapter, what is electrical energy? That I am going to explain. Okay? Electrical energy means, for example, and this is any circuit or for some resistance or anything, and this resistance is connected to some battery, right? And this is a battery, and now this is the battery voltage is V, and there is some plug key. This is the plug key, and now here you know already the current flows from positive terminal of battery to the negative terminal of the battery, but electrons flows from negative terminal to the positive terminal. And when the battery is doing some work, to pass the current through the resistor, right? And then that work is equal to electrical energy. And here some energy, battery supplies some energy to the electrons to travel along the circuit. Then the work done by the battery, to pass Q charge, to pass electrons through the circuit, electrons through the circuit is equal to electrical energy, Okay, the battery have the chemical energy that will convert into electrical energy, and that will convert into current. Current energy is the electrical energy. And now this electrical energy formula I want to write. Then this is electrical energy is equal to the work done by the battery. Is it right? Electrical energy is equal to work done by the battery. But what is the work done by the battery? Yes, we know the potential formula. Potential is equal to work by charge. You know potential difference. V is the potential difference of the battery. Then work by charge. Then work is equal to what you will get? Potential difference into charge. That means now electrical energy formula is equal to work done by the battery. But work done is equal to VQ. What is V here? V is the potential difference. And Q is the charge. Okay? Q charge. And now this is the electrical energy formula, but according to Ohm's law, right? Or according to current charge equation, right? But current formula is what? You know? Yes, current formula is Q by T. From this charge formula we write IT. This we substitute in above equation. The electrical energy, another formula we will get, right? Electrical energy formula we will also get is VQ, but Q is IT. Then VIT we will get, right? VIT we will get. And here, but according to Ohm's law, right? According to Ohm's law, do you know Ohm's law? What is Ohm's law? Tell me. According to Ohm's law. What is the Ohm's law equation? Potential difference V is equal to IR, right? I is the current, R is the resistance, that we substitute. Then electrical energy, another formula we will get here. Electrical energy, another formula we will get is, right, V is IR. IR into IT we will get, that is I square RT we are getting, right? And again in place of, okay, here in place of V we wrote IR into IT. IR into IT is I square RT. Electrical energy we got I square RT. And we can also write this formula, electrical energy is equal, finally we got I square RT, right? I square RT. Here according to Ohm's law, what we write the I? Can I write I is like this? V by R whole square into RT, right? Because we know according to Ohm's law V is equal to IR, I is equal to V by R, this we substitute. Then what you will get the electrical energy? One more formula. Yes, V square by R square into RT. This R square will cancel. Then electrical energy, one more formula is, right, tell me, what is that? V square by R into T. We wrote several formulas we derived for the electrical energy. I will combine and I will write, okay? Electrical energy is equal to, firstly what we got? Work done by the battery. Work is what? Potential into charge. Because potential difference equal to work by charge. Work is equal to potential into charge. We take Q to left side, then W equal to VQ we will get. This is earlier in in lecture number 2 we discussed that one, right? Okay. In the previous video, potential difference we discussed, right? Potential difference equal to work by charge. W equal to VQ, right? Electrical energy equal to work. Work is VQ. VQ we got, but the Q current formula is Q by T, charge by time. From this Q equal to, we take to T to left side, Q equal to IT. Here we substitute in place of Q is IT, right? In place of Q we substitute IT. I is the current, and in place of V according to Ohm's law, IR we write IR into IT, I square RT. And in place of I, V by R we write, according to Ohm's law, then V square by R into T. These are the various formulas. These are the various formulas for the electrical energy. The work done by the battery is equal to electrical energy. Work done to pass I current or to pass Q charge through the circuit, that work done by the battery equal to electrical energy. These are the various formulas for the electrical energy. In this, what is I? What is V? V is what? Tell me. Potential difference. Potential difference. Potential difference. We already know this one. V is what? Potential difference. Potential difference. What is Q? Charge. What is I? Current. What is R? Resistance. R is the resistance. What is T? Time. Right? T is the time. Okay. This is the electrical energy. What is the unit of SI unit of electrical energy? SI unit of energy. Right? Already we know in the 9th class, energy unit is Joule, right? If you want the full name, Joule, Joule we have to write. If you want to write symbol, capital J we have to write. Okay? Joule. And one more unit also there, other unit. Okay? Other unit is also there. Electrical energy unit is watt hour. Watt hour. Okay? This is WH. Or kilowatt hour. Kilowatt hour. kWh. Right? This is the other unit of electrical energy. I will tell what is watt hour and what is kilowatt hour later. And now in this class only I will tell. And that are the other unit of energy, just like Joule only. And now this is about electrical energy. And now let us discuss about the electric power. What is electric power? What is electric power? Okay, power formula in the 9th class we discussed, right? Electric power. Power means what? Power. The rate of doing work is called as power. Power equal to work by time. At what rate the work is going on. For every second, how much work is done. That is called as power. If you do more work in the less time, then you have the more power. Okay, work per second. In 1 second, how much work you are doing? For every second or for every unit time, how much work you are doing? That is called as power. The rate of electrical work. The rate of electrical work. Rate means the rate of electrical work done. Okay, the rate of electrical work is called as electric power. Electric power. We can also define in another manner, right? Or electrical work per electric work. Okay, electrical work per unit time. Work per unit time. In 1 unit time, how much work is done? Right? Electrical work per unit time is called as power. Okay? And now the power formula is work by time. Okay? Power formula is work by time. But work we have to take electrical work. Okay? Then the power is equal to work formula is what? We know already work various formulas. That work is equal to, we know potential into charge, potential difference into charge. Okay, and now this we write here VQ by T, right? And Q by T is what? I is equal to Q by T. We write VI. The power formula is VI. Okay, power formula is VI. And this we can also write as V is equal to IR. We write V is equal to IR. We write. Then what you will get? I square R we will get. I is equal to V by R. We write I is equal to V by R. V by R into V. V into V by R. V square by R you will get. How you are getting this one? This one we are getting from V is equal to IR. Okay. And from this, in place of V, this is the power formula, V into Q by T. But Q by T is the current formula, I equal to Q by T. But here VI we got. In place of V, I substituted the IR. IR into I is I square R. In place of I substituted the V by R. V into V by R is V square by R. This we substituted from Ohm's law. Okay. And here already we know VIT, I square RT, V square by R into T. This is electrical energy. Electrical energy is nothing but work only. Work formulas are VIT, I square RT, V square by R into T. Work by time. This you divide with the time. This you divide with the time. This you divide with the time. VIT by T, VI. I square RT by T, I square R. V square by R into T by T, V square by R. These are the various formulas for the power. Okay? Power formulas. Just power, how you will get? This power equal to work by time. But work is also equal to energy, right? Work is also equal to energy. That means power is equal to work by time. Work is equal to energy, right? Energy by time also you will tell. Right? Energy formulas here we got. That you divide with the time. Then you will get the power formulas. Then let us see here. Power proportional to resistance is there. Power inversely proportional to resistance is there. Power is what? The rate of electrical work done or electrical work per unit time. Where the work is done? To pass the charge through a resistance. Okay, this is a resistor. To pass some current and to pass the electrons through it, some work should be done. And that work is the electrical work. And for every second how much work is done, that is called as electric power. Or this battery energy and battery power this resistor uses, right? And now let us see the power SI unit I want. SI unit of power. SI unit of power. What is the SI unit of power? You know already. The power unit is watt. Watt is the power unit. Symbol is capital W. Okay. 1 watt is equal to what we write? 1 watt is equal to. We have the power P is equal to V into I. You know this is the basic formula. Then power we write as 1 watt. 1 watt is equal to, this V is the 1 volt, and the current we write as 1 ampere, right? Then 1 is equal to 1 you will get P1 V1 I1. 1 is equal to 1 into 1, 1 you will get. V unit is volt, I unit is ampere. 1 watt is equal to 1 volt into 1 ampere. 1 watt is equal to 1 volt into 1 ampere. Then how to define the 1 watt? Definition of 1 watt. Okay. Power consumed by an appliance when 1 volt potential difference causes the 1 ampere current in it. Okay. And this is the definition of 1 watt. Now let us continue. Electrical power unit we got is watt. Okay, once again I will tell the definition of power. Look at here. The power unit is 1 watt. Okay, the rate of electrical energy or the rate of electrical work is called as electric power. And here the power unit is watt. Definition of 1 watt is, definition of 1 watt. 1 watt equal to 1 volt into 1 ampere. 1 volt is the potential difference, 1 ampere is the current. For example, when we say that the power is 1 watt, power is 1 watt. For example, here we have a bulb. Okay, we have a bulb. Now it consumes some power, right? For example, 1 watt power, when it will consumes. If for example we are sending 1 ampere current through it, 1 ampere current, and through a potential difference of 1 volt, then power consumed by it is 1 watt. That means when V is 1 volt, I is 1 ampere, then power is 1 watt automatically. That means the power consumed by a device, the power consumed by a device, consumed means absorbed. Okay, this is electrical power is absorbed and utilized, and it is converted into other forms by the device. Okay, for example, here we have the electrical bulb. It extracts the electrical energy from the battery and it will convert into heat and light energy. That means now it is utilizing the energy, means it is utilizing the power, and that power consumed by a device when 1 ampere current passes through it under the potential difference 1 volt. Look at here, the power consumed by a device, that carries how much current? 1 ampere current when a potential difference equal to 1 volt, when 1 volt potential difference created across it. Okay, and the power consumed by a device that carries 1 ampere current when it is operated at a 1 volt potential difference is called as 1 watt. Okay, and now the power consumed by this device, okay, bulb, that carries how much current? 1 ampere current. When it is operated under the potential difference 1 volt, the power consumed is equal to 1 watt. Means we have to send 1 ampere current at the 1 volt potential difference. At that moment the power consumed is equal to 1 watt. Now this is the power unit. The next other unit of electrical energy I will tell. We have the other unit of electrical energy, that is watt hour or kilowatt hour. How it is there, and let us see here. And for that, it was very simple to understand. What is the formula for the power? Right? The power consumed by an appliance. The power consumed by an appliance. What is the power? Okay, power is equal to work by time. Work is equal to energy by time. That means now electrical energy consumed formula, right? Electrical energy formula in terms of power we can write, right? Electrical energy formula. Electrical energy, right? Power is equal to work by time, energy by time. Do we take time to left side? Then energy is equal to power into time, right? Energy is equal to power into time. Then from this energy unit we write from this formula power unit into time unit. That means watt hour we take, right? And high powers we can take in another unit, other units of power. Other units of power, first we write the other units of power, later we write the electrical energy. Other units of power, there are other units are there. Okay, other units of power. Other units of power is kilowatt. Kilowatt. Okay, this is kW. kW. Here 1 kilowatt equal to 1000 watts. Megawatt. Megawatt. MW, capital MW. Mega means 10 power 6 watt. Okay, and other unit is horsepower. Horsepower is also unit of power. Okay, and 1 horsepower is equal to 746 watts. Okay, and here large power measured in horsepowers. Okay, large power measured in horsepowers. Okay, motor power we write motor power, right? 1.5 HP, right? 2 HP, like this we write horsepowers. 1 horsepower equal how many watts? 746 watts. Okay, and here for example incandescent bulb. Okay, generally the bulb on every appliance there is some written power will be there. Power will be written, will be there 60 watt like this, 60 watt bulb, 10 watt bulb. Nowadays LED bulbs we are getting, in that wattage is very less, 10 watt bulb, 20 watt bulb. Here in previously incandescent bulb, filament bulb will be there, that has large power 60 watt, 100 watt like this. What is the meaning of the 60 watt bulb? 60 watt bulb means what? Okay, this is a bulb. Over this there is some written value will be there, right? Over this it is written as 60 watt and 220 volt, right? And that means this bulb operates at potential difference 220 volts and the power is 60 watt. 60 watt bulb means 60 watt bulb means bulb consumes 60 joules energy per every second. Okay, for every second bulb consumes 60 joules energy per second. In 1 second 60 joules it will utilizes. That means 1 watt is equal to, we know, 1 joule by 1 second. Is it right? 1 watt is equal to 1 joule by 1 second. How? This is power is equal to work by time. Then power is 1 watt, work is 1 joule, time is 1 second. Then 1 is equal to 1. 1 watt is nothing but 1 joule by 1 second. 60 watt is nothing but 60 joule by 1 second. 60 watt is equal to 60 joule by 1 second, right? 60 is equal to 60, 1 is equal to 1. That means now 60 watt is nothing but 60 joules energy it is using for every second. That's why in monthly we are getting the some bill and we have to pay because we are using the electrical energy, right? On every appliance, right, there is written value is there, that is the how much power it can consumes and how much at what voltage it will operate, that will be written, it will be there. Okay, and now for example here motor has electric motor, water motors are there, pumping motors in bore 2 HP or 1.5 HP. 2 HP motor means what? 2 into 746, right? That is 2 6 ja 12, 2 4 ja 8, 2 7 ja 14, right? 1492 watts energy, that means watts power, that means 1492 joules per every second. The motor 2 HP motor consumes 1492 joules energy for every second. In every second this much energy it can consumes. This is the meaning of power. How much energy consumed in 1 second, that is only called as power. Power means energy consumed per second. We can also define like this: the power consumed is equal electrical energy consumed per second is called as power. Okay, we can also write like this: electrical energy consumed per second. In every second, how much energy consumed? Electrical energy consumed per second is called as what? Power consumed. Okay, is called as power consumed or the power, right? In every second, how much energy consumed, that is called as power. And this is about electrical power. And now electrical energy, another units are commercial unit of electrical energy is what? Generally we will get the bill in every month because we are using the electrical energy. In our home we have so many appliances, right? Every appliance uses some energy, right? Electrical energy. Then for that we have to pay the money. Then how they will calculate the electrical bill, right? Let us see how they will calculate our electrical bill. Now for that, commercial unit of electrical energy required. Commercial unit of electrical energy. What is the commercial unit of electrical energy, right? Commercial unit of electrical energy. Kilowatt hour is the commercial unit of electrical energy. Okay, what is our commercial unit of electrical energy? Kilowatt hour. Let us see. Then kWh. Okay, this is kilowatt hour is the commercial unit of electrical energy, not joule. But we have to use kilowatt hour, we have to use. Okay, or sometimes watt hour also we will use. How this? Okay, we have the power formula, right? Work by time, work is equal to electrical energy by time, is it right? Work is equal energy by time. Then what you will get the electrical energy from this? Can you write? Yes, electrical energy is equal to power into time we will get. Okay, this is the electrical energy formula, that is power into time. And now based on this unit, okay, unit of energy from above formula, can you tell? Right, you can tell very easily. Yes, energy is equal to, what is that? Power into time. Power into time. Power we write watt or kilowatt we also we can write. Okay, watt, megawatt also we can write. Power units are kilowatt, megawatt, horsepower, watt. There are several units are there. Power unit is kilowatt. Into time unit we write second, minutes, hour also we write here. Okay, this is kilowatt into hour, right? Kilowatt into hour we write, right? That means now from this we write as other unit is kilowatt into hour. That means this is equal to kWh, or watt hour also we write. Okay, kilowatt hour or watt hour. Then this kilowatt hour is the unit of energy. Power into time. Power unit you write kilowatt, then kilowatt hour. Kilowatt hour or watt hour are the other units of electrical energy, right? Other units of electrical energy. Watt into hour, kilowatt into hour, megawatt into hour. These are the other units of electrical energy. Kilowatt hour or watt hour. This is R. Okay, are the other units of electrical energy. Now, how to convert this kilowatt hour energy unit? Also we know joule, but we how to convert this kilowatt hour into joules? 1 kilowatt hour equal to how many joules? Okay, and convert 1 kilowatt hour into joules. Joule is the unit, then kilowatt hour to joule we want to convert. 1 kilowatt hour is equal to 1 kilowatt hour is equal to 1 kWh is equal to, we write 1 kilo into 1 watt into 1 hour we write. Okay, then what is 1 kilo? 1 kilo we write as 1000 10 power 3 into 1 watt we write as, power formula we have work by time. Work power unit is 1 watt we take, W is 1 joule we take, time is 1 second. 1 watt equal to 1 joule by 1 second. Right, 1 watt is equal to 1 joule by 1 second we take. Okay, 1 hour also we can convert into seconds. 1 hour, to convert 1 hour into minutes we have to multiply with 60. Right, to convert 1 hour into minutes, to convert 1 hour into minutes we have to multiply with 160. And next, to convert hours into second, one more 60 is there, 60 second, right? This will cancel. Then what you will get? 60 into 60, 3600 into 10 to the power of 3 joule we will get. Okay, and here what you are getting? 1 kilowatt hour is equal to 1 kilowatt hour is equal to, we are getting 3600 into 10 to the power of 3 joule we are getting. Okay, look at here. Convert kilowatt hour into joules. 1 kilowatt hour is equal to, what you are getting here? 3000, 16 to 60, 3600, 10 power 3. 3600 into 10 power 3 joule we are getting. This is 1 kilowatt hour is equal to, this we write as 3.6 into, or 36 into if you want, right? 36 into, this is 10 power 2 we write, into 10 power 3 we write. Then this we will get as 1 kilowatt hour is equal to 36 into 10 to the power of 5 joule we will get. This we can also write as 1 kilowatt hour is equal to 3.6 into 10 power 6 we write. Because this I am writing as 3.6 into 10 into 10 power 5 joule. Okay, this is how to convert kilowatt hour into joules. You must remember 1 kilowatt hour equal 3.6 into 10 to the power of 6 joules. Kilowatt hour is a unit of energy and joule is also a unit of energy. That's where kilowatt hour converted into joule. If 1 kilowatt hour energy used, then we say that it is equal to 1 unit. Okay, 1 kilowatt hour is equal to, we can take as 1 kilowatt hour, 1 kilowatt hour, 1 kilowatt hour is equal to, we take as 1 unit. Okay, 1 kilowatt hour is equal to 1 unit. Okay, n appliances. Okay, n appliances, each of power, n appliances each of power p are used for time t, then energy consumed, then electrical energy consumed. What is the formula for that? Electrical energy consumed, how you will find out? That is, electrical energy is equal to, what is the formula? Do you know? Yes, you know. Electrical energy is equal to, what is the formula? Power is equal to, we have energy by time, work by time. Work is equal to energy by time. Then energy is equal to power into time. Energy is equal to power into time. Then energy is equal to power for one appliance. One appliance means, for example, one bulb is one appliance. We have 10 bulbs, means n is the one bulb is a one appliance. One bulb power is 60 watts. Like that we have the 10 bulbs, means n is the number of bulbs. N appliance each of power. One bulb power is p. N bulbs power is np. One bulb used in time t, right? And the time is t. Every bulb used for the time t. That's why np into t. This is the formula to find out the electrical energy, right? N is the number of appliance, p is the power, and t is the time used. Okay, and now here this energy, if you get in the kilowatt hours, that kilowatt hour energy equal to 1 unit. 1 kilowatt hour energy equal to 1 unit. For example, in government will decides, for example, for every unit 2 rupees. Then for example, in 1 month, if you used the 60 units, then 60 units you are using. For every unit they will take the 2 rupees. 60 unit means how many rupees bill you have to pay in the 1 month? At 1 unit 2 rupees, 60 units, 60 into 2, 120 rupees bill you have to pay. Like this they will calculate the electric bill. How they will calculate the electric bill? Based on the number of units. How you will find out the number of units? First you find out the electrical energy. Electrical energy you can find out. Electrical energy in terms of kilowatt hour you can find out. That kilowatt hour equal to units, right? For example, here you got the electrical energy. Electrical energy is 10 kilowatt hour. But 10 kilowatt hour equal to unit, means 10 units. You have to find out the energy. Energy formula is what? Power into time. Very simple. Then easily we can find out, right? And now this is about electrical energy and electrical power. Energy and power we discussed. And let us continue. How to define the watt hour definition? What is the definition of watt hour? Watt hour is the unit of energy or power? Tell me, what is the unit of WATT? Watt is the unit of power. Watt hour is the define 1 watt hour. Define 1 watt hour, right? Define 1 watt hour. 1 watt hour. Okay, how to define the 1 watt hour? That I want. 1 watt hour is equal to what? Tell me. 1 watt into 1 hour, right? If 1 watt appliance, okay, 1 watt power appliance used for 1 hour, then energy consumed equal to 1 watt hour. Watt hour is the unit of energy consumed, right? Watt hour or kilowatt hour. Watt is the unit of watt or W, unit of power. But watt hour or kilowatt hour, okay, or joule, these are the units of, tell me, energy. Very good. Right, now let us see how to define the watt hour. How to define the watt hour? Watt hour is the energy consumed, right? The energy, electrical energy, the electrical energy consumed by 1 watt appliance used for 1 hour is called as 1 watt hour. 1 watt hour. Okay, 1 watt hour is the energy consumed by 1 watt appliance in 1 hour. 1 watt power appliance, 1 watt bulb is there, that is used for 1 hour. Then energy consumed equal to watt hour. Energy is equal to watt hour, power into time, right? And let us see next. I am going to explain the one more topic, that is heating effect of electric current. Okay, the next topic is heating effect of electric current. Heating effect of electric current. Heating effect of electric current. How to find out the heating effect of electric current? Heating effect of electric current. Okay, when current passes through certain resistor, this is a resistor, when current passes through it, okay, if the I current passes through it for time t, at that moment when the electrons are passing through the resistance, when current goes to right side, electrons goes to left side, then these electrons collides with the ions. Okay, this resistor opposes the motion of electrons. How motion is opposite? Then ions will be collide. If collisions are more, then the resistance is more, right? And now here, due to the collision, some heat develops across the resistance, right? Whenever the current passes through a resistor, across the resistor heat develops, right? On what factors that heat produces, that we are going to discuss, right? Okay, when current passes through a resistor, heat develops or heat produces across it. Heat produces across it. How much heat produces? Right, heat formula is what? Heat energy produced. Heat energy is equal to work done by the battery. Work done, okay? Energy is equal to work done. Then heat energy is equal to work done, means heat energy is equal to, work formula is what? Yes, potential into charge, or V equal W by Q, we know, right? V equal W by Q. From this, W is equal to what you will get? VQ we will get, right? Heat energy equal to work is equal to potential difference into charge. Charge we can also write VIT, and V we write as IR. I square RT we will get. IR into IT, I square RT we write. We can also write V square by R into T, right? We derived the different work formulas, that all work formulas are equal to heat energy, right? And look at here. Finally we got heat energy formula, one formula. There are several formulas are there. In this one formula, we will use the H equal to I square RT, okay? And that is called as Joules law. Heat energy heat energy, that is equal to I square RT, right? That is H is equal to I square RT. This is called as Joules law. Joules law. Okay. What is the Joules law? Let us see here. Joules law of heating effect. Joules law of heating effect. Let us see. In heating effect, Joules gave some law. Then what is that law? Right? And heat energy formula is I square RT. On what factors this heat energy depends? That is given by the Joule scientist. Let us see the first point. The heat energy produced is depends upon the current. Okay, this is a resistor. This is a resistor or the heater. Okay, some current passes through it. Across this heat develops. Right? Across this heat develops. That heat energy produced across a resistor is directly proportional to the square of current. That means now heat proportional to I square. H proportional to I square. Look at here. Heat energy proportional to square of current. If current is more, if you send the more current, then more heat develops. If you send the less current, then less heat develops. Right? If you send the less current, then less heat develops. Right? And the next second point is that from this heat produced directly proportional to the resistance. Heat produced is directly proportional to the resistance. H proportional to R. If resistance is more, opposition is more. Opposition is more means, okay, for example, this is a resistor, and when electrons are passing like this, these electrons will collide with some ions. Due to the collision, some energy loss of kinetic energy occurs, that will appear in the form of heat. Okay, if resistance R is the resistance, if R is more, then I is more, H heat is more. If R is more, right, then H is more. If R is less, then H is also less. Next, heat energy produced is also directly proportional to time. Right? Heat produced directly proportional to the what? Time. Proportional to the time. That means H proportional to T. If more time, if you send the current, more time if you send the current through the heater or resistor, right? And the more heat will be develops. This is the Joules law. Let us see some practical applications of heating effect. Practical applications of heating effect. Where we will use this heating effect. Okay, for everything you take the screenshot and write the notes, and if you have any doubt you can consult me. Okay, and let us see practical applications of heating effect. Practical applications of heating effect. What are the practical applications of heating effect? Where we will use practically this heating effect? When current passes through a resistor, heat develops. That heat where it will develop and where we will use practically. Okay, let us see the practical applications of heating effect. And practical applications of heating effect I am going to tell where we will use this heating effect. Now this we will use, for example, this is a resistor. Okay, when current passes through this resistor, what happens? Heat develops. Heat develops. And where we will use this practically? Right, in our home also we will use electric laundry iron. This will use the nichrome wire, electric toaster and electric kettle. Right, you know these all things. These are simply we are using in our homes. Laundry iron, iron box, kettle for preparing the tea, and electric heater for heating the water, right? And these are all we will use, okay, for the heating elements. Electric oven, okay, that also you know egg puff, curry puff can be heated by using electric oven, that is a micro oven bolte, right? And these are the some applications. Electric laundry iron, these are all uses based on the heating effect. Electric heater we know, electric laundry iron we know, when current passes through the nichrome wire. Nichrome is a wire, okay, it is an alloy. Alloy means it is a mixed metal, okay, and that will, when current passes through it, okay, in that heat develops. That heat we will use to iron laundry iron or to cook the food items and to prepare the tea, electric kettles, and to heat the waters, right, electric heater. These are the some heating effect applications when heat develops, and that will be used in these instruments, right? And for that instruments we will use the nichrome wire. And another is bulb. We know very well about this bulb. Okay, incandescent bulb, filament bulb, let us see. That filament bulb we will give the supply the current, means we will give the electrical energy, that will convert into the heat energy and light energy also, this bulb. This is the filament bulb. In this tungsten filament will be there. This is the tungsten, right? This tungsten filament has high melting point. Okay, this tungsten filament has, this will convert across this when current passes, right? Heat develops, along with that light develops. When current passes through it, heat develops. When heat, due to the heat, temperature increases with the time, and when it heats to large temperature, and this can also generate the light. Okay, and this has tungsten filament, tungsten. It is also alloy of metal. Okay, this tungsten has high melting point, means it is heated to large temperature. What is the temperature? 3380 degrees Celsius it has. Then at this temperature it can be melt, and that means it has very high melting point. And now generally at our room temperature is about 25 degrees Celsius. In summer it is 35 degrees Celsius, nearly 45 degrees Celsius. That means the range is from 20 to some 42, 43 range will be there, the room temperature, the heat outside temperature, atmosphere temperature. But here this one is at very high temperature. Even at high temperature also it cannot melt, right? And to melt it, very large temperature is required. Its melting point is 3380 degrees Celsius. Because here large heat develops, even though it should not melt. If it will melt, then what happens? It chooses, it cannot work. This tungsten filament should not melt, that's why it should have high melting point. And this bulb, it is heating and it is also generating the light. Due to that heat, the atmosphere and surrounding should not be burned. Then to protect from that, this bulb is completely filled with some inactive gas. That inactive gas is, what is that inactive gas? Okay, that is inactive nitrogen or argon gas is filled in the bulb. Then due to that, the lifetime of the bulb also increases. And the next one, this heating effect application, one more application. In these all things heating effect is used, and in the bulb also heating effect is used. In the fuse also we will use the heating effect. What is the fuse? Okay, for every appliance have small fuse. In our home also fuse will be there. Suddenly due to some reason, if large current enters into our home, okay, when large current enters into our home, and then every appliance will damage. To protect the appliances from the large current, we will use a instrument that is called as fuse. A fuse is a device that can protect the appliances from the large current. Okay, that is also depends upon the heating effect. When current exceeds certain value, then it can melt. For example, and this is a fuse. This is a fuse. This is a fuse. And now this is the main wire. Okay, and this is some connected to some appliance. Okay, and now when current exceeds certain value, then what happens? If current, for example, this appliance requires only 5 ampere current. Okay, every appliance requires some current. If this current exceeds 5 amperes, okay, if current exceeds 5 amperes, then fuse will melts. Fuse melts means then current supply to the appliance, current supply stops. Okay, current supply stops. Fuse melts means this wire will melt, then connection will be break. When connection will breaks, at that moment the current supply stops, then appliance is protected from the high current. If you use the 5 ampere fuse, more than 5 ampere, 6 ampere fuse, if current passes 6 ampere or more than 6 ampere, then it can be melted, right? And here, for example, if this appliance requires only 5 amperes, less than 5 amperes requires. More than 5 amperes if it will comes, then it will damage. To protect from that, we will use a fuse. This fuse, if current exceeds 5 amperes, then automatically this fuse will melt and current supply will stops. Like that the fuse will operate. The fuse protects the appliances from large current. When large current enters into our home, right, it directly cannot supply to the appliances like a tube, fan and television, refrigerator. Directly it cannot supply that large current. What it will do? First it will enter into the fuse. When current exceeds certain value, automatically the fuse will burns. When fuse burns, the current supply to the home stops. Then all the appliances are protected. Like this fuse protects the appliances from damage from the large current. Okay, and the last topic, and with this our chapter will complete. The last topic is advantages of parallel combination over the series combination. What are the advantages of parallel combination over the series combination? Right? What are the advantages of parallel combination? The topic is advantages of parallel combination over the series combination. Whether all the household appliances, TV, fridge, television, bulbs, fans, whether these are all connected in parallel or series, in our home or in everywhere we will connect in the parallel. Why we connect in the parallel? Because on fan, on tube, on television, every appliance, okay, in our home, all appliances require the same potential difference, that is 220 volts. Every appliance, on every appliance you see the fan, and over that it will be written, it will be there 220 volts, some power it is written. On the bulb 60 watt 220 volts. On the television also some 220 volts. That means every appliance requires only potential difference 220 volts. That means same potential difference is possible only in parallel combination, right? And that means in parallel combination, what is the advantage? All the appliances operate at the same potential difference, right? Same potential difference. You know, in parallel potential difference is constant, right? In parallel combination potential difference is constant, but it is not possible in series, right? It is not possible in series. In series it is not possible. Potential divides. Different potentials will be there. In parallel combination, all the appliances operate at the same potential difference. The second point here, the first point is that the potential is constant. This is the advantage. The second point is that potential is constant in parallel, right? In parallel combination, which is constant? Potential is constant, right? Potential difference is constant. Potential difference V is equal to constant. And in parallel combination, okay, we have different appliances, fan, tube, and television. Different appliances have the different resistances. Different resistances means they require the different currents, right? Different appliances have the different resistances. Different resistances means different current requires. Then that different current is possible only in parallel combination, because in series combination same current passes, right? That means different appliances has, okay, different appliances have different resistances. And they require different currents. It is possible only in parallel combination, right? Only in parallel combination it is possible, right? In series combination same current passes. In parallel combination current divides. Then according to instrument, which instrument require how much current, based on that the current will passes. And the next third point is that in parallel combination we use the different switches for the different appliances. Is it right? In parallel combination different appliances in parallel combination, every appliance has its own switch, okay, but it is not possible in series. In series all the appliances have only one switch. In parallel different appliances have the different switches. Look at here, this is for example first bulb and this is the second bulb. What is this combination? This combination is parallel. Here we will use one plug, one switch, and here we will use one switch, okay, and different appliances have the different switch, right? Different appliances have the different switch, but this is not possible in series. In series like this it will be there R1 first bulb and this is the second bulb, and here we are connecting like this. Current starts from here like this. Here one switch we will use, okay, but here it is not possible to use the different switches. Here we will use one switch, and if you will use here one switch it is useless. If you open this switch then automatically current not passes to this side. No use of this cell. That means different appliances not have the different switches in the parallel series combination. And one more point is the last point. If one appliance fails to work, in parallel, then all the remaining appliances continues to work, but it is not possible in parallel. But it is not possible in series. But it is not possible in series. In series, if one of appliance fails, then all the remaining appliances cannot work. For example, this is a bulb. Okay, we have this is a bulb, and this is another bulb. This is a battery, right? And this is series combination end to end. For example, this bulb fuses. That current starts like this, but the current never passes to the other bulb. That means in series combination, if one bulb fails, then okay, because current supply stops. We have the decorative in the marriages or in functions. We see the decorative bulbs like this. It will be there, like this. If one of the bulb fails, then other will not work. Right? It is very difficult to find which bulb is not working. And in the parallel combination, like this it will be there. This is the first bulb, and this is the second bulb. These are in parallel, and this is the battery, right? For example, this bulb fails. Okay, this bulb fuses. The current starts from here like this, and current never goes to this side, because this side path it will become open circuit. Okay, current flows only in closed circuit. This side current never flows, but there is a chance to flow this side, right? Like this. That means here this is only one way. In the one way, if anything is closed, then we cannot go forward. But there are two ways are there. If one way fails, then other way is there. That's why if one appliance fails in the parallel combination, then other appliances will continue work, right? And these are the advantages. The same only disadvantages. What are the disadvantages of the series combination over the parallel combination? They will tell. In the series combination, potential divides. In series combination, same current passes. Right? We can write reversely for this. Right? In series combination, we cannot provide different switches for the different appliances. In series combination, right? If one of appliance fails, then all the other appliances will not work. These are the disadvantages of the series combination over the parallel combination. These are the I gave advantages first, and they may ask the disadvantages of the series combination. Advantages of parallel combination. Parallel combination is advantage, series combination is disadvantage. Right? Why? They may ask, write the advantage of parallel combination over series combination, or write the disadvantages of series combination over the parallel combination. Right? And why series combination is not used in the household appliances? In home, why we will not use the series combination? In our home, why we will not use the series combination? You can answer. This answer you can give in the comment. Thank you for watching my lectures. And I made the lengthy lecture. You can split half an hour. First you can see and take the screenshots and note it. And if you will get the doubt, and go back and revise the video, and then you will understood. Even though if you not understood, you can make a phone call, or you can WhatsApp me, you can contact me, and complete all the lectures. Okay? And I made the 5 lectures for the class 10 electricity. 1.1, 1.2, 1.3, 1.4, 1.5 with this. And with this we completed our first chapter. Okay, you can complete your notes, okay, and take the screenshots and write the notes, and also complete the in-text questions. I will make one special video for only problems. I will make the NCERT exercise problems one lecture I will make. Don't worry about that one. And we will discuss total problems in that topic. And one time you write all the formulas in one page, okay? And then after that we will discuss one lecture for the problems, specially problems. And those who not subscribed till now, you must subscribe and press the bell icon. And if you not watch the previous lectures, okay, lecture starts from electricity, how to see the lectures, you open my channel, and in that first line, home, placed, and videos, placed, about, something will be there. In that placed you can click, in that there are several chapters are there. Class 10 electricity you can select. Class 10 electricity 5 lectures are there, 1.1, 1.2, 1.3, 1.4, 1.5, in order it is there. Then in that you start from 1.1 and watch all the lectures and take the screenshots and write the notes and complete the in-text questions, and NCERT exercise I will explain one time. Okay, thank you for watching my lectures.